Autonomous experimentation, that's such an interesting term. It sounds interesting, right? It just rolls off the tongue. But it's something that's incredibly difficult to do, but it's also increasingly important to do and to do well. And there are very few people, in my estimation, who are doing it well right now in the US or in the world. And we're lucky to have one of the people who I think is at the forefront of this field, I'm certain is at the forefront of this field, with us here today. So Keith, I'm going to introduce you very briefly. The floor is yours. Keith is coming to us today from Boston University in mechanical engineering. Okay, and I'll allow him to tell you about his program, and hopefully we can all learn a great deal from it. So welcome, Keith. Sure.
All right, all set? You can laser point. Thank you. All right, well, thank you all for the wonderful introduction and for the invitation to be here. It's really fantastic to be at the start of something exciting. I'm really was impressed by the forward-lookingness of this proposal, and I have to say it looks like a very exciting time to be a graduate student here at Penn. So congratulations to the team putting this together. And so what I'd like to do today is give you a bit of an overview of my work in the area of autonomous experimentation, a little bit about the field, and you know how I think if this also might be a little bit of a primer if you're a graduate student here and you're thinking about, you know, is this something that I should be afraid to jump into? Is this something that I should be that's difficult? Maybe this is an invitation to join this field, and something this is very, very welcoming. If you know experimental science, this is an easy transition to make. But if you think about big picture, why are we interested in this in the first place? Why do we care about autonomous experimentation? Our motivation is probably very similar to the motivation of many of you, which is that we are making materials too slowly to meet the challenges we're facing as a society. Let me give you some examples of that. So if you look at the pace of materials research, so one example that I like to point to is, so in the 60s, working at DuPont, Stephanie Kwolek invents Kevlar. Fast forward about a little more than 20 years, in 1987, one of the most advanced formulations we have, Kevlar 149, becomes available, hits the store shelves. So two things about this that I want you to pay attention. One is the sort of 20 or so year gap between the discovery and the hitting the shelves. And the second is that we're still using this type of Kevlar today. We don't have better materials than this, nearly 40 years later. So that's too slow of a pace of progress. It's too slow to develop these materials. It's fair to say, okay, this is the 60s and the 70s. Things were slower back then. We're better at this now. Well, let's consider a more modern example. Let's look at graphene. So 2004, Gaiman and Vasilov isolate graphene for the first time. It sets off this extraordinary wave of materials research, probably the most studied material in this century, if not really, maybe ever, in terms of papers published. 6 years later, they win a Nobel Prize. So how long do you think it took this material to get into commercial product? Modern material, most studied material, perhaps ever. 1 year, right? Some ambitious company jumped in here. So 15 years, we'll see, good estimate. So if we look, the first product that I was able to find, so in 2013, you could buy a tennis racket with graphene in it. Now that's a little gimmicky, there's no proof that actually improved the properties. The first product that actually used the properties of graphene wasn't until 2017. Not bad, good guess. This is why you win proposals. And so yeah, modern material, highly studied, we still are very slow. And so this observation, it takes far too long to go from discovery to application of material, has really been one of the driving factors of what's called the Material Genome Initiative. About 12 years ago, it was put together in the founding document. They say that at present, the time frame for incorporating new classes of materials into applications is remarkably long, typically 10 to 20 years from initial research to first use. It's too long. We have too big of problems. This is especially true in soft matter. And I want to dive into that a little bit deeply. I'm going to talk about pretty much mostly about polymer research. So let's talk about why getting new materials in polymers is so challenging. And the short answer is there's too many things you have to choose. So in polymer research, the first thing you have to decide is what polymer you're using. So what is your repeat unit chemistry? And there's a lot to choose from. There's basically infinite possible choices you could make here. If you restrict yourself just to the things that have been widely studied, so you go to a database like PolyInfo and look at how many homopolymers you can find, there's thousands, so it's 7,000. Once you've chosen that, you still have to make more choices. For example, you put that together into a macromolecule. You have to choose, do you use other repeat units to make a copolymer? Do you make it a linear? Do you make it branch? Change the topology? How long do you make it? You could also ask, so once you've chosen this macromolecule, you have to choose the microstructure. And you do this by deciding what kind of processing you're doing, if you're adding additive, if you're blending other polymers, do you cross-link it, what temperature you use. All this affects things like the crystallinity of the material. And then furthermore, once you've decided on this scale, you have to decide how you're going to use this on a larger scale. At a larger scale, now you're architecting the material more broadly. Maybe you're going to make a composite with other phases of matter, and maybe you're going to treat the surface. And so there's all of these scales, and each one of these scales individually could be a research program, could be many research programs, could be a society, could be a field. And yet, all of these things together determine the properties that we have to use these materials. And to add to this complexity, if we think about how we measure these things, we have to do experiment. Often we'll have simulation proxies at many of these scales, but the best, in some cases, the only way we can assess these is by doing physical experiments. So how do we do this? Well, if we want some inspiration of what we could try, a few months ago, we saw this sort of jumping into the field of large language models really give us this AI is here to stay. And there's actually an interesting parallel here between polymers and these kinds of structures. For example, if we look at repeat unit chemistry, maybe we could think about these repeat units as letters, right? And then we put them together to make macromolecules. Maybe that's like making words. Take those words, put them together. Maybe that's like writing sentences and paragraphs, and put those together into a macrostructure. Maybe that's like writing a book. And so we've seen that if we have good, if we have these models like ChatGPT, we can make some really amazing strides here. So the question is, why can't we do this with polymers? And I would argue that, well, so if you look at what it took to get these large language models, we have terabytes of labeled data that go from the individual letters to the whole book. We do not have that with polymers. We are lacking the data we need that's labeled across all these scales to have this kind of insight. And so I think the key thing that's missing here is the data. And so if we can find ways to get transformed into more data, perhaps we can address this problem. And so how are we getting data currently? Well, when I was a graduate student, and in many places around the world, the typical way research is done is this iterative cycle where a person chooses an experiment to do based on their intuition, the literature, what they're thinking about that day. They do the experiment, they interpret it, they repeat this process. And there's two things about this process that I think are not efficient. The first is that it's slow, and the second is that it generates data that's not comparable, and it's very difficult to grow in a consistent way across decades. And so a different way of thinking about this that we've been pursuing in my group and other groups around the world in the past few years is this idea of autonomous experimentation. So here's the simple idea, is that we're replacing a person doing an individual experiment with robots doing experiments in mass. So this can be high throughput, it can be done reliably, and all this data is inherently compatible. It's born digital, as actually was said in this room in an autonomous conference 4 years ago held by Eric Stack. So this room has a very interesting history in this autonomous field, showing that Penn has made a sustained investment, which is very cool. But so the robots doing the experiments here, and then those are being, second experiments are iteratively chosen using machine learning algorithms. And so this sort of cycle is what's known as a self-driving lab, because you give it a goal of some kind, then it progresses towards that goal. And it's not just operating in isolation. It's in principle possible to say, take information from the world and put this in so it moves faster. Or take information from this out so this can serve as part of a broader design perspective if there are experiments you want to do that you cannot simply do in an automated fashion. So this can become a part of a broader materials development ecosystem. And so what I'd like to do with the rest of my time here this morning is to talk about how my group's been exploring these concepts in the past few years, particularly, really all of these different pieces. And we've been working in this field in kind of three different areas that I'll talk about that really span the length scales of polymers. At the largest scale, we're studying how we can use additive manufacturing to make mechanical structures and tune their emergent mechanical properties for extreme mechanics. In this, we're using 3D printing and robotics. And the intermediate scales, we're studying how we can make polymer thin films using electrodeposition to tune transport properties for applications like battery electrolytes. And then at the very smallest scale, we're putting materials together to make compositional gradients to study how the chemical factors influence things like mechanical properties for resins and for 3D printing and such. And so what I'll talk about today, just to focus on is this area, this first area, because this is the area where we've been working in this autonomy space for the longest time. We have the most lessons that connect to autonomy that I'd like to share. If you're interested in these other areas, I'm more than happy to talk to you about them afterwards, so don't hesitate to come up and chat with me. And so in this space, we have to start with what motivates us to do autonomous experimentation in the first place, or experiments at all. And this is something I think you need to ask, and in complex fluids, this is very obvious many times, but why do you need to do experiments in the first place? And in the mechanical world, the answer is extreme mechanics and absorbing energy. And so we are ourselves in our daily lives surrounded by the materials and structures designed to absorb mechanical energy. Now, normally when I say that, people are sitting in chairs that have foam on them. These chairs do not have foam on them, so perhaps in the future we could benefit from that. But basically, from things like crumble zones in cars to protective foams in personal protective equipment, things like this, or the packaging and things when you order something off Amazon, these are all designed to absorb mechanical energy. And they have a huge range of operating environments. So, whether stiff or compliant, or whether used once or multiple times. However, they all share a few notions that really tie them together, design themes. And that's that their job is to absorb as much energy as possible while not damaging the thing they're trying to protect. And so let's dive a bit more deeply into that kind of dichotomy. And so if we think about a typical material, a protective material in compression, so we have some force displacement curve in compression, the curve is going to look something like this. We have some region in the beginning that we would call the elastic region. It's pretty easy to pick, and then it sort of flattens out and then grows. And so to absorb as much energy as possible, what that means is we want to have as large an area under this curve as we can. However, we can't do this infinitely. We need to protect something that we need to basically not surpass some threshold value of force. If we go beyond that, we'll destroy the material. For example, a crumple zone, if we go beyond some force, we'll crumple the passenger cab of the car. And so this is the design challenge. And so why is this hard? Well, we can predict a lot about this very easily. If we look at, for example, the elastic region, we know how to predict that very well based on structure and properties. We know how to predict this region here. That's called densification. That's when you have basically some foam-like material and you've squeezed all the air out of it. You just have a puck of material. We know how to predict that. The problem is that middle range. Now, the middle range exhibits this complex interaction between the material starting to become nonlinear, the structure becoming nonlinear, interactions with the two reentrant contacts, all sorts of things that are difficult to predict, and more importantly, strongly determine the energy absorbing capacity. You can see that crossing this line is all too easy or going very far under it. And so this is a very critical region, and we have to test this. The most reliable way, in many cases, the only way to test this is using experiment. So how can we improve on this? How can we improve on the design of this? Well, in the past decade or so, people have gotten very excited about using things like additive manufacturing as a way to design materials for energy absorption because it presents just huge amounts of design freedom. And so if we look at some recent literature, here are some examples that I've taken from the literature that look at people that are 3D printing structures in one way or another for their ability to absorb mechanical energy. Here's an example of some carbon nanotubes that are laser sintered, some metal structures. Here's some auxetic lattices that are printed out of polymer. And then a very recent example that came out just, I think, a week or two ago about some ultra-high energy capacity lattices that are made out of the copper and gold. And so all of these are really, really interesting works, present a lot of unique ideas. One factor that when you look across that is unified is that all of these things, if you look at the data underlying these papers, which have the words like energy absorption in the title, they all feature on the order of 10 or so experiments. And that's because these experiments are slow to do. And so usually you might do some simulation design, but of course that only gets you halfway, then you validate with experiments. So this is going to be a process that relies on very small amounts of experimental data. And so we want to overcome this. We want to find new ways to study these that allow us to have much more data. And so going back to this picture I showed you earlier of performing experiments and choosing experiments, let's look at each of these in detail and see if we can improve on them. Starting with performing the experiments. And so this is the challenge I posed to my group a few years back. So can we improve on this? And what we came up with was this system that's shown here. It's a robot that includes 5 3D printers. These are fused filament fabrication printers. They're in the working range of a 6-axis robotic arm. The arm retrieves parts once they're printed. We weigh them. We put them in an Instron universal testing machine to compress them until failure, and the process repeats. And this happens without any human intervention. We test, depending on the kind of campaign we're running, between 50 and 100 experiments per day. It's been running, more or less continuously since about 2018. So we've been running this for a while. So you could say, okay, so we've got this automated system. It can crank through lots of experiments. We can get lots of data. What can we use it for? And by the way, I'm very interested, if you're interested in the sort of nitty gritty of how to make something like this work, I'm more than happy to talk about that later. There's a lot of subsystems here that are interesting. Things like, well, if a printer bed has some stuff on it, what happens? Well, it turns out that the arm actually grabs a scraper and scrapes the bed. And it figures out it needs to do that with machine learning or machine vision. So there's a lot of things beneath the hood going on here that make it run reliably. In the last 2 years or so, we've had about 85% uptime over the entire year. It worked when I was having Christmas dinner. And my students weren't working, more importantly. So this is working, all the time. So what do we get by having an automated system? So the first thing we can do is to say, well, let's think about when you design something digitally, what you might do is called a parametric design. You have a parameter space, you find out the values of the parameters that are best, and you use those. So let's think about an experimental parametric design. So we came up with an idea of how to do that. We designed this class of structures we called cross barrels. There's about 500,000 distinct structures in this 4-dimensional design space. So here we basically take a cylinder with some radius and thickness, we put n of them in a circle, and we twist them by some amount theta. And this gives us a wide variety of possible mechanical responses. For example, we can have cross barrels that are very weak, they're brittle, so they fail rather quickly and then have no strength after yielding. We can have those that are too strong. If we think about this design constraint I talked about earlier, you can't go above a force threshold. We can have those that are so strong they go above the force threshold, so they're not considered. Here the force threshold is about 5 kilonewtons. And then we can have those that absorb quite a lot of energy. And so here we have one, you can see that after yield, it has a relatively flat behavior, and that's because you have these reentrant contacts that occur once yielding begins that allows it to preserve its mechanical strength. So we have this parameter space. How can we explore this with a robot? Well, what we're going to do is we're going to just try to map the whole space directly. And we have a large experimental budget. So here's a representation of that space. It's a 4D space. I can't show you 4 dimensions, but I can show you slices. And so each of these panels shows you the radius versus the theta angle here. And as you go to the right on these, you get to thicker columns. And as you go down, you get to more columns. So this shows you really the whole space. And so we can simply divide this up and say, okay, let's study this whole space. Let's build a grid, study 600 points, test them in triplicate. Why not? So we do 1,800 total experiments. And in doing that, we can map this space. And so this is what we get. And you can see that the regions that are blue are low performing. Regions that are yellow, they're high performing. And so it's a complicated space. We have a lot of hills and valleys. The best regions are those that are yellow, so down here. And so if you look at what this predicted to be the very best in this space, we find that it's this one. Okay, so we were able to use this robot to exhaustively map the space and find a very high-performing cross barrel for these considerations. Could we have done this better? This is what you might call the brute force approach. And so to do this better, we have to go back to this picture. So we've now used a robot to test things in automated fashion. Can we improve on the way we're choosing our design? And for this, there's a lot of different approaches you could take. We're going to take the approach of Bayesian optimization. Now, this is an algorithmic way of choosing experiments that allow us to iterate towards a given goal. And to explain how this works in more detail, I'd like to show you kind of a cartoon example of this process as it goes. And so to show you that, here's an example of what you might say. So if we have some response surface, the blue here, that we'd like to find the maximum of. Now, we don't know what this is. We might call this the ground truth in a machine learning context. The only way we can interact with it is by doing experiments, these observations, these red dots. And so our goal is to choose experiments. And so the way we're going to do this is a two-step process in Bayesian optimization. The first step is we use a surrogate model, which is basically we take the existing data and any prior knowledge we have, which I can talk more about later. We take that existing data and we use that to build a probabilistic model of what we think the function looks like. And that has two pieces. The first is that we have this green line that shows the expectation value, the mean of that probability distribution. And you can see that goes through these points in this case. And we also have this green bar around this. And this shows us the uncertainty, because this is a Bayesian framework after all. So this is our belief for what this function looks like. You can see right now it's not particularly good. But the other thing we have in this framework is the ability to use what's called a decision-making process. Now, this is the way of selecting the next experiment algorithmically based solely on the model we've collected so far. And the way this looks is we take basically what I showed you on the previous slide, and we apply some policy to it. Now, I'll tell you about the policy, expected improvement policy is a particularly popular one these days. And what this policy does is it prioritizes sampling in locations where it thinks that we're likely to find a better result than we've ever found before. So we're expected to improve on our best result. And so looking at this, you can see where it's evaluating these. So this is the region here it's evaluating is very good in terms of expected improvement. And that's because the function value is all right. It's pretty good, but really it's because we have a lot of uncertainty here. And so this is a really key feature of this policy and many policies like it, which is it's balancing natively these competing notions of exploration and exploitation. So let's see what happens. So this is the choosing the policy, but let's turn the crank around this loop. So we do that experiment, we update our model, and so now we have this kind of curve shown here. And you can see now we're going to move off to the left is where we want to sample, and this process continues. We iterate, and two things happen as we approach the end here. The first is that, of course, we find a very good value for the maximum. So from an optimization standpoint, we've succeeded. But more important than that, in my view as a scientist, is that we now have a belief that matches the ground truth function. And so we've learned the function. And so under appropriate conditions of uncertainty, we are balancing exploration and exploitation, or learning and optimization. And so let's do this in practice. Let's use this in practice. So I'm going to take the robotic system I developed before, and we're going to add to this a loop that allows it to take the data that it's learned. You feed it through a machine learning algorithm and select the next experiment. Again, all happening without any human intervention. And so we name the system the Bayesian Experimental Autonomous Researcher, mostly because in this field it's very important to have catchy names. So we called this the bear. And so I'll show you as a campaign of the system running. And we have the same space I showed you before. And so we're going to randomly seed it with 1 point and then allow it to explore the space. It knows nothing about the space ahead of time. And just to give you a preview, this is the point that we found was the best point from our exhaustive grid search. And so I'll start the movie. And you can see that as the points are coming in sequence, it does two things. One, it kind of branches out from where it started, exploring, but it also spends a lot of time, say, here and here, regions it finds to be good. So it's natively balancing this exploration exploitation. And so at the end of these 100 experiments, we can ask, well, where's the best result that it found? Well, it turns out that it found that one down there. So who's right? I mean, grid says you're over here. this campaign says we're over here, so who's correct? Well, this is, an experimental function. The only ground truth we have is experiments. We have to do experiments. So we're going to take those two values, and we're going to do 10 experiments in each point. And what we find is that where our grid-based result, we got 35 joules, and for that campaign, we got about 40. So we got a marked improvement. We're using 18 times fewer experiments, and we repeat that same process 2 more times, we get about the same result. Showing you that, if you are selecting each experiment based on all the knowledge you have so far, you can do a lot better than this sort of simple grid-based searching. And so this, when we published it back in 2020, had a couple of important distinctions. And the first was that this, was really the first experimental benchmarking of a self-driving lab, because we really compared experimentally what you can get by, grid-based searching, say, and this Bayesian method. And also it was really the first self-driving lab to use Bayesian optimization in the first place. But this is really in many ways a toy, because what we're taking this system, this cross-barrel system, we're just trying to find a maximum just to explore how these things work. But you think about from mechanics context, we're doing this optimization. Really, it's what you call a black box optimization. We're pretending we know nothing about this system. We're just trying to find the best values. Now, in reality, we'd like to think we know some things about most systems we're studying. In mechanics, we have a lot of knowledge about the equations of mechanics. One way to formalize those is, for example, using simulation, so finite element analysis. So you could say, can we use that knowledge in some way to seed this process to make it go faster? And so that's what we wanted to explore next. Can we accelerate this process using prior knowledge, in this case, simulation? And so the short answer is yes, but the long answer is more complicated. And so if we think about the functions I've been talking about before, so this is the kind of response function that we have of one of these cross barrels, of one that's reasonably tough. And you can see that, the post-yield behavior is very complicated. If we look at what we can simulate, now we're by no means world experts in simulation, but going beyond this is very challenging. But we can simulate very easily the elastic region, the point when it starts to yield. And that really just represents the tiny little beginning sliver of this result. So we can't simulate the whole thing, but we can simulate the beginning bit. So let's do the easy thing first. Let's say, well, we can simulate that bit in the beginning, which is called the resilience. Can we learn on that? Well, resilience itself is important. That's how much energy you can absorb and then give back. So it's useful when you're developing materials for springs and returning energy. And so, can we predict this well? Well, it turns out, yeah, the simulations match experiment very well in this regime, which is shown by this kind of nice parity line. So let's learn on this. And so to explore this idea, we built an experimental campaign around it, where we took the same bear I showed you before, but we're going to use the finite element analysis as a prior in our belief model. So we're taking that Bayesian optimization. We're saying it's supposed to start by believing simulation's right. And what we do then is we learn the difference between the simulation and when the experiment predicts. So we're not starting with nothing. We're starting with simulation as our belief, and we're learning the correction to it. This is an idea that's borrowed from the DFT community, where they do this idea of delta learning, where you can have high and low fidelity simulations, and you want to learn corrections to your low fidelity simulations using your high fidelity simulations. And so this is this approach, this delta learning approach. And what we find is that, so whereas the grid-based search, returned about 1.6, in just 3 experiments, we've found more resilient structures using this system. So 600 times faster than you might find on a grid. And furthermore, if you compare it to the bear without any prior knowledge from simulation, it takes 30 experiments for it to catch up. So even against that, we have a 10-fold improvement. So showing that we're having dramatic acceleration. So if you have a good prior, if you have an idea of what your function should do, use it. It's going to help you dramatically. But what if you don't? What if the more interesting case you don't? These are all the really rich cases that we're studying. So we talk again about the toughness. If we look at specifically at toughness, we can't predict this. We can't predict, there's no correlation between the resilience we predict and the toughness we measure. So how do we use this? Now, this actually ended up being one of the most scientifically fulfilling parts of this research. Now, I'm sure you guys all got these questions when thinking about this, but there's always this tension in this field of autonomy where you say, are you trying to replace graduate students, right? Are you trying to build a robot that does the experiment? And so my answer is that it is much more interesting and enlightening for students to work on the kinds of problems I'm about to talk about than it is for them to do 1,000 experiments. And so let me tell you about how we approach this. Because the question now is, how do we use a simulation of an unrelated thing to predict something that we want to learn? And let's build a hypothesis about that and have the bear test it for us. And so we came up with 2 ideas. The first was, looking at this force displacement curve, we can predict the yield force well enough. So the question is, well, we know that if things are too strong, they're not useful. The yield forces are too high. So let's use that one as a barrier to say, if the yield force is too high, we're just going to throw those points out. We're not going to consider them an experiment. We're going to filter those out. So that's one. The second thing we did, I think, is conceptually much more interesting, which is to say that if you know anything about toughness, you probably know that it's kind of balancing 2 considerations. For something to be tough, it has to be strong, so it has to go high on a force displacement or stress strain curve, and it also has to be reasonably ductile. And those are generally competing ideas. The materials tend to only get one or the other. And so one thing we say is, well, we can we can predict the strength well enough from simulation. So what if we just try to learn how ductile the structures are? And so what we do is effectively, rather than thinking about this complicated force displacement curve, we conceptualize this thinking about it as just kind of a rectangle where you know the height of this rectangle based on the yield force. And we basically learn how ductile the structure is. And so we believe, just based on our simulations, this should have longer correlations in parameter space and therefore be easier for our experimental system to learn. And so when we do this, we find this is the results of a campaign where we ran 60 experiments. This is again on toughness or total energy absorbed. It turns out that it only took us 60 experiments with the naive bear without simulation, to match our predictions, our grid. So this is kind of what we think that in terms of acceleration against this grid-based searching, we usually say a factor of 30 based on this number. But more importantly, if we give the bear the simulation, we find is that on average, we have a 15% improvement over the performance of the bear without simulation. And we find structures that were the very best we had ever found in this entire parameter space. So showing you that it's both faster and more effective. And so this was, a very important, I think, lesson, because it showed us that, we can use this approach to find structures very efficiently. We have ways of bringing data in. And so, this kind of took us to the end of this cross-barrel story. And at that point, we kind of sat back and think, okay, well, we had this parameter space. It was 500,000 possible structures. We studied 3,000 or so of them. And what we learned at the end of the day is we only really needed to have studied 30, and we would have gotten kind of as much out of this space as we needed to. And so that kind of made us think, well, could we do more with this? And one obvious thing to think about is, well, we actually did in many ways, a small slice of the challenge that we set out for ourselves here. Because if you think about the cross barrels, we were setting one force threshold, one material, one consideration. Now, in the beginning, I told you there's all sorts of different materials that one could choose, and they all have different thresholds that you might think about. So the question we wanted to ask is, we find a way to generalize this approach to solve it in a much more broad context. And so for this, we need to change our thinking in a few important ways. The first thing I want to highlight is we changed from thinking about components, in terms of their force displacement, to try to think about effective materials. And to go there, we're going to talk about stress and strain. So we're going to use effective stress and strain of these materials. So you're thinking about effective medium approximation. And when we do that, the first thing that jumps out at you is the strain, goes to 1. And this is because when you have a material in compression, you can't compress it more than 100% strain. No material left. And one thing that jumps out from that is if you look at the stress threshold, that forms a box, where this box represents the very most energy you could possibly absorb if you had a perfect material. So that's our theoretical maximum. And you can also look at any given component and say that this actually, where it intersects this defines this blue shaded region. That's what we actually absorb. And those two things together allow us to define one pretty simple, conceptually simple scalar. This is how efficient is this structure at absorbing energy. And so we define this as Ks. It's defined in analogy to Ashby made a similar term back in the 90s looking at impact efficiency. People have used similar things in the literature. You might see this as different kinds of E and eta, but it's basically an efficiency that describes how well it's absorbing energy at a given stress. But more important than perhaps looking at any given stress, we realized that actually thinking about this allowed us to take the complexity of this entire part and distill it down to one pair of numbers. Because if we look at this stress threshold, this value threshold, if the threshold's too low for the part's going to be elastic in this entire region. So it's not going to be very efficient. And if the threshold is too high, then this material or component is going to be comparatively low because you're going to have this empty space above it that you're not capturing. So there's actually, if you look at any given material or structure, there's generally one point where this is maximized. And that point defines, first of all, how efficient this thing is at best, and also where you should use it, what sort of operating condition it's ideally suited for. And those two things together define a given component. And so with this kind of new lens, we said, okay, we'll see how we're doing. We'll see how people do in terms of this efficiency. So we turn back to the slide I showed you earlier. These are the mechanical structures I said. Again, these are all 3D printed structures designed for energy absorption. And if we look and compute their Ks values, their efficiencies, they tend to range from about 20% to just below 50%. Including structures that, this is a presumably world record holding structure in terms of mass efficiency. It was only 30% efficient from this metric. So, we think there's probably a lot of room to grow on this. So, but let's also look a bit inwardly. I showed you 3,000 experiments before. How did we do? Well, these are all the cross barrels I studied. So here we have this metric Ks. I'm looking at the range of the different efficiencies or the different stress values they can obtain. And you can see that it tops out at around 51%. So, okay, we did slightly better. But is there room to go from this? So we find examples of materials that are much better than this. Well, the best synthetic material we found is a foam that you can purchase called Rohacell, which is about 68% efficient. Beyond that, we can say, well, is that the best thing we've ever found? The best thing we found, period, was nature. We've yet to beat nature, which is balsa wood, which is just under 72%, so 71.8% efficient, and by one report. And so, okay, there's a large, we have a lot of room to go, but we kind of get to the 50s with 3D printing. Nature gets to the low 70s. And also another challenge to bring up is that, I showed you this is the cross barrels. This is a relatively narrow range in working stress. Ideally, we would like to optimize over a much, much larger range. So the next insight we had to bring to the table to sort of figure out a way to improve this is, well, the first obvious thing is let's not just use one material. All the work I showed you previously was this one polylactic acid, PLA, which is a common 3D printing material. Let's broaden the scope. So we basically went and ordered every possible filament we could think of, giving us a wide range of these different materials. And now, if there's any 3D printing aficionados in the room, you'll know that once I start telling you, okay, I want to run a robot that prints NinjaFlex, which is a soft filament, and I want it not to jam for a week straight, and you're going to say that doesn't sound possible. And so that's a major challenge. How do you ensure printability for components that are out of soft materials, or really any experimental filament? And so to address that, luckily, a graduate student joined my team, Kelsey Snap, who's a 3D printing expert, had the insight that conventional printing is this layer-wise process where you print and you stop and you print and you stop as you add layers. The stopping and starting, that's the problem, because if that allows you to jam. And so instead, there's this mode called spiral mode printing, where you continuously extrude. So you're continuously raising the nozzle and extruding as you go. Now, this is great. It's much less prone to jamming. The problem is, if you can call this a problem, topologically, what you're making is a cylinder, because you have to never stop. You can't cross. And so this, you would think, sort of limits what you can make. But fortunately, we teamed up with Emily Whiting, who's a computer scientist at Boston University, who helped us figure out a way to address this. So normally when you have a cylinder, you can think about it as being defined by how tall it is, how wide it is, and the thickness of the shell. But we work with her to develop a family of structures by changing the parameters at the top and the bottom, amounting to a total of about 11 different knobs we could turn. And these collectively allowed us to realize what we're calling generalized cylindrical shells. And by our count, in terms of what we can print, there's on the order of 10 or so trillion of these. So we're talking about a substantially larger parameter space than we had access to before. So I want to show you the result of us exploring this parameter space using the bear. And so here's a movie of that. We're going to show a movie momentarily about this happening. I want to explain with the slide a bit first. So again, we have KS vertically here. This is our efficiency and the working range of stress across the bottom. And so we're going to optimize over a large range. So we're going to go from the bottom 100 pascals to the top to 100 megapascals. Now this is a room full of soft matter people, so you probably actually know what 100 pascals feels like. That's the weight of a quarter sitting on your hand, right? This is very, very low stress. At the high end, 10 megapascals, if you want to know what that feels like, imagine that same quarter with a horse standing on it. That's sort of the range. And again, the graduate student, Kelsey, these numbers were worked out for a male Arabian horse, if you're keeping count. So just to be clear. So this is a pretty wide range. And so what's our target? Well, if you think about common materials, so typical foams you might purchase off, say, McMaster are going to range from 30% or so to 40 or so 50%, depending on the stress you're looking at. They're generally more efficient as they allow them to become plastic higher up. And the two records I showed you before, the best synthetic and the best natural structure, are shown here. So I'll show you a movie of these data points coming in. To date, there's about 12,000 of them, so they're going to come in batches, but they're coming in the order they were collected. The color corresponds to the different points. Here they are coming in. And I want you to pay attention to how progress is made, because this is a really fascinating part of the study for us. This campaign's been going for about 2 years at this point, and what we've learned is that progress happens in fits. And there's two reasons for this. One is serendipity, where you might have the robot makes a discovery and then starts following up on it, and that ends up with great progress. And the other is that we look at what the robot's doing and we change our perspective, we change the algorithm it's using, and that also ends up resulting in some large jumps as well. And so you can see, you just saw the result of one such jump where we got to this sort of low 60s, and then past that and got into the 70s, and now we're sort of filling up in the low 70s. And then, and most recently, we sort of, as the points come in, we got up there to about 75%. And so we are able to overcome this record. And to show you an example of a component that reaches this limit, here's a component that's 75.2% efficient. This movie's a little dark. It'll lighten up when I play it. But this is a movie of the compression event. Of course, all the compression events we're doing have movies attached to them. Here's this result. And you can see that it has this really fascinating response where, this is a PLA part, actually, still PLA coming back. But you can see this material kind of folds up, like it almost looks like, it has this really interesting re-entry in contact. You can tell it is plastically deforming quite dramatically. And it becomes this really extraordinarily flat curve that shoots up dramatically, showing you that, we have this extreme efficiency. And this is, what it takes to design something to reach this record. And so, we were very excited when we found this. We believe this is the most efficient structure or material ever realized, and so we're very excited about it. But it also, like, the questions like, well, how general is this? I mean, if you wanted to make something out of a different material, would that be useful? Would it work as well? And so that led us to think about this a bit more generally. And so I'll tell you the results of exploring two different parts that were found in different places in the space and whether they're general or not. Here's, we named them after trees, by the way. Oh, question.
Is this completely dissipative? I mean, so you're measuring energy absorption,
yeah.
but do you look at what sort of strain you can recover after you unload?
We do. Actually, as a matter of fact, when one of the things about the automated process, we test the parts, we lift up the platen, and we come down again to see how much, if they've had any recovery. But generally, a part like this, and actually this is generally true for anything high efficiency, it's definitely plastic. This is completely crushed.
Any stored elastic energy?
Oh, no, yeah. I think I see your point. Okay. We do not subtract any stored energy. Yeah, this is just the total area under the curve. So that would, yeah, that in principle, I see your point. You could, if you had gone to just this point and then back out, it might give some of that energy back. Whether that's good or bad, it's not clear. But yeah, but in order to look at this, we really have to try to measure as much of the force displacement or stress strain curve as we can. So we can't turn around midway necessarily. But that's a great question.
I mean, in applications, do you actually care about that stored energy? I mean, that can sort of come back, like if you're making something for ballistic protection, that stored energy is potentially harmful. You want to dissipate as much as possible and store as little as possible, right?
Yeah, that's true. I think those are both very good considerations. I mean, you could definitely imagine. You can estimate to some extent stored, like best, or sort of just based on the elastic portion of the curve, you can estimate some of what the stored energy would be. But I do agree with you that if there could be considerations where this could be harmful. This particular component I wouldn't worry about storing too much energy, as it ends up being quite flat. But yeah, I see your point though completely. Great, though. Thanks. And as we go to the more elastic structures, they do store a lot more energy, as you see. But okay, so looking at trying to see if these are more general structural motifs or if these are just, we found some optima of this printer and this material. So we looked at two different designs. We named these after trees, just to give us a lot of variety. So for example, willow is one very similar to the one I just showed you. It was discovered in PLA. It has a pretty flat force displacement or stress strain curve. And on average, it's about a little over 73% efficient. We can compare this to what we call Hierarchical, which is a part that's first discovered in a thermoplastic polyurethane material. And this has it tends to have about a little under a 55% efficiency. Turns out that the more elastic materials, thermoplastic elastomer is a more hyperelastic material. These aren't as efficient for reasons that are kind of come from the mechanics. So we could ask, well, does a part that's good in TPU look good in PLA and vice versa? And so here's the results of that. So here we have the efficiency of components as against the Young's modulus of the filament that we produce them with. And what you can see is this interesting kind of crossing sigmoidal curves where, for example, our willow part performs very well with PLA and PTG, similar kind of glassy plastic materials. And as it goes to the more elastic materials, it becomes less efficient. Correspondingly, our Hierarchical part is very efficient when we look, or is very highly efficient when we look at the very elastic parts, and becomes less efficient as we go up to the more glassy parts. So we do see that these geometries seem to be consistent among classes of materials, which allows us to be optimistic about the design prospects of this. And that kind of leads us to this question of, well, we have this huge library of materials and results, so what can we learn from this? And so one thing we can learn is, well, can we provide any guidance for design? And so if we look at kind of, here's a plot that shows you this is the efficiency versus the working stress of really all of the parts that we've studied for two different materials. So this is the same thing that made Hierarchical, that thermoplastic elastomer. This is the same thing that made Willow, that PLA. And you can see what's highlighted are their kind of design envelopes, the regions you can design. One thing that kind of jumps out at you is that, if you look at where they're peaked, there's really one value where they're peaked, one value in the stress. So for a given material, there's a region in this space where the material is most efficient. And we can zoom in on this and say, well, some other classic things you could do from a materials perspective. You could build an Ashby plot, look at, say, for example, the relative yield stress or the relative strength of the material versus the relative density. You typically see that, less density, these are sparser parts, end up being less strong. And you could look at the power law here. This tells you our power law is about 1.36. So the properties are kind of giving us something between the buckling regime and the elastic and the stretching regime. So it's kind of what we would expect for these kinds of structures. But this also highlights that, but we can compare this to the strength seems to change rather gradually, but we can look at there is an optimum strength. So how do we compare those two ideas? Well, it turns out that there's a optimum density. We want the parts to be low density because if they're low density, the densification strain can be very, very low, which is important for efficient parts. And so there ends up being a maximum of the KS as a function of relative density. That means that you kind of want to park right here at about 10% density. And we can kind of look more generally to think about, well, how do people tend to think about these mechanical structures? Well, in the worlds of cylindrical shells, we tend to think about, okay, if we have properties like the thickness, the height, and the diameter of these kinds of components, can we just look at how these properties matter? And we can look at our 10,000+ data points and say, here we have this efficiency versus some aspect ratios. For example, how wide the part is relative to how tall it is, or how wide it is relative to its thickness. And when we see in both cases, we have optima. And these, we're digging into these increasingly, but with these come down to basically in the cylindrical buckling world, it's known that there's sort of competing ideas of trying to manage the buckling that can show up by allowing it to have interesting reentrant properties. And so allowing us to sort of tune these values allow us to find interesting locations here. And so these leads to kind of interesting design philosophies of, for components to be high performance, we want their diameter and their height to be commensurate. We want it to be roughly 40 times larger than its thickness. We want it to have a low relative density. And then for a given material, we want it at a working stress that's around 50 to 200 times less than its yield stress. So it really provides a lot of interesting design ideas here. And so this is, when you have a data set that's 10,000+, it allows you to do this kind of large analysis very easily. And so, more to come on this. And also, you could ask, well, how can we go from a component to a material? Well, that's another area we're currently exploring, and one way to think about doing it is to change the printing process to allow us to include solid materials. This is one idea that we're developing on with our computer scientist colleague Emily Whiting, where we're building these sheets into these materials as we're printing them, allowing us to have large-scale structures extending in 3D. So this is an example of how we've been able to sort of iteratively work in this parameter space to find components that to both get some mechanical lessons, and then also find components that provide some basically break a world record, we believe, in the area of mechanics. I want to talk about one more idea just briefly in the minute or two I have left to talk about, I've been talking about how we can sort of turn this crank very much, but I also want to talk about the output of this, because in many cases, we have the experiments we can do easily in an automated fashion, but we often want to predict something else. We want to learn something else from this. So how do we systematically take data out of this loop and use this to predict other properties? And the property I want to talk about briefly is this idea of impact performance. So impact is a much more complicated thing to study than quasi-static performance, because you have a lot more degrees of freedom to change, the mass, the velocity, etc. You also have larger samples typically that are destructively tested. This is an example of a testing of a bike helmet, for example. This work originally was started in our group because we're developing helmet pad materials. And so going forward, we say, okay, well, how can we accelerate this? Well, the way this is typically done currently is an iterative process. And to study that process, we developed a set of generalized lattices. These are also 3D printed, but we're using a stereolithography process rather than fused filament right now. And the process that we're doing here is, what we typically would do is we'd choose a design we think is good. We would test it. This is what the result of the test is. We have an acceleration versus time plot. Typically, what you care about is the highest value of the acceleration. This is when the damage would be done. This is what a given experiment would look like. We have an anvil falling on this, and there it is. It would ricochet off. You'd see that, and that's the energy return, as was mentioned. And then we'd use this to build a model of the, this maximum acceleration as a function of our design space, and we'd find our minimum, say, and that would be our design process. But this is slow because this experiment here is slow. And so how do we accelerate that? Well, we have to leverage the fact that we have a huge amount of data that's collected by other means. And so in particular, we developed an approach where we basically take the same parameter space, and we can test using a high throughput method, this quasi-static testing, which we can do robotically. We can generate hundreds and hundreds of curves of different structures in the space, not designed to optimize anything specific, but really just designed to explore the space, get a sense of everything that's possible in this space. We can then select things from this space and then test them in this sort of slower process to get this iterative design. And then compare the results of these to basically build a machine learning model, which I'll talk more about on the next slide, that describes our predicted performance that just comes from quasi-static measurements against what's measured in the impact. And then this allows us to build, and this is really the important part, a measure of how is the impact performance dictated by the forces we measure in quasi-static. Because that means we can design things without doing the complicated experiment. And so what that looks in practice is we do, about 100 or 800 or so quasi-static measurements. We use unsupervised learning techniques to boil this down to 3 parameters that we can use to describe any given force displacement curve. We then use those 3 parameters along with our 140 impact test to build a model that allows us to predict impact performance generally. And this is the result of that kind of approach. Here we have the predicted performance using quasi-static measurements versus the measured impact. And when the training data is the blue and the gray data, and we have good cross-validation error here, about 13%, which is commensurate with the variation we see in experiment. But more important than that is when we validate this, we can look at structures that are not at all in our training set. For example, we looked at these octahedral and octet lattices in our training set. We designed a whole lot of other things that were not in that set. Well, how do we put them into this model? It's because the model isn't based on a geometric parameterization. It's based on a force displacement response. So if you tell me a force displacement curve, I can use this model to predict acceleration. So it's a very general design tool and also compatible with inverse designs. You can say, what kind of force displacement curve should I get to have good in performance? So this is, what came out last year. Very excited about this work is it allows us to have this very general design tool, and it's powered by data that comes from the self-driving approach. And so to take us to the end here, I want to give you some ideas of some of the key lessons we've learned when we think about this kind of loop. Well, the first thing is that if we use automation, we can get data as fast as possible. It generates large amounts of data. That itself isn't enough, though. We need to use algorithms that allow us to choose experiments more productively, and that allows us to converge more quickly towards a given goal. Do that a lot, get to generate large databases that can be useful both to find high value points and also to get data sets that are more value in general. And then data can be fed into this whole system using, say, simulation or other data sets and be extracted to predict other things. And in this way, there can be a more general there can be a more general materials development pipeline in which this self-driving approach fits into nicely. And so I think I'm short on time, so I'll skip some of my other concluding remarks just to end. Oh, okay. Well, we're not short on time, so I'm not going to skip any remarks. The first thing we've learned is that we can really transformatively accelerate polymer research using these self-driving labs and associated approaches. A lesson that I'm sure that as more autonomous experimentation here becomes sophisticated, you will learn as well, or if not already. Some examples of this, some concrete things we've discovered is we've done benchmarking that shows that this approach is 30 times faster, and this is just in terms of numbers of experiments. If you talk about wall clock time, we're able to achieve in a day what would previously have taken months and months and months of time in terms of actual wall clock time. So that's a very huge reason to take this approach. And then having these systems allows you to do things you would never think possible before, perhaps. For example, in our case, our crusade here to find this most efficient component, which we believe we've accomplished. And then we've allowed this to more generally fit into a materials development pipeline. Take data in, bring data out, etc. And we think that's even when you can't study, the thing you want to study is not itself the end product. I think this provides a lot of value. And I think if you're talking about this as a scientific tool, oftentimes, you don't need to have the end product. You can do a lot of work on model systems, and that gives you a lot of insight. So there's even more value here. And then other efforts in my group include using this approach to do things like develop thin film materials or to study polymer chemistry. And so, I think maybe the biggest take-home message, though, is that when we're faced with this sort of insurmountable dimensionality that comes with soft matter, which comes with polymer research in particular, our only real tool here is to get a lot of high-quality data that's well chosen. And I think the important way to do that is to use these kind of self-driving labs across scales and have that data amalgamated in useful ways. And that will take me to my most important slide, which is, of course, to thank the people that did the work. And so this is the students. You've heard a lot about the PhD work from Aldair Gongora, who's now at Lawrence Livermore, Kelsey Snap, currently in the group, and a lot of others. We have a lot of external support we're very appreciative of, and collaborators have been very helpful. And I think David is sort of ducked out, but I wanted to acknowledge him in particular. So he was my graduate student mentor when I was a graduate student, but also in his parting week of being in the research group, he gave a literature talk on what is now regarded as the first self-driving lab, this one out in London. So he was actually my first exposure to this topic back in that day. So he missed that, but that's great. But anyway, so thank you very much for your attention. I'd be happy to take questions as time permitting.